friends. Today we're going to talk about gasoline production from Group 2, Zaki Maulana, myself, Vika Aurelia, and Shafira Fidelia. Next slide, please. Okay, so what we're going to talk today is introduction of gasoline production, isomerization, catalytic reforming, alkylation, and polymerization. Next. So for introduction, the demand for motor fuel or mogas increased. Hence, many early refining processes were built with conversion in mind in order to boost gasoline production. Gasoline has a carbon number ranging from C5 or carbon 5 to carbon 12. Distillation can be used to get this fraction as straight-run naphtha. However, not all naphtha molecules have high enough octane ratings to be used in automobiles. One strategy would be to isomerize and reform into structures with high octane ratings without changing the carbon numbers. Other methods include alkylation and polymerization to combine carbon 3 to carbon 5 molecules, or cracking and coking to reduce the size of carbon 12 plus molecules. Next. Moving on to isomerization process, isomerization catalyst consists of aluminum chloride or AlCl3 supported on alumina with hydrogen chloride gas as a promoter. Many conversion units in the refinery undergo isomerization of bigger and paraffins. It's extremely important in catalytic cracking, which may yield linear olefins both with and without extra hydrogen. The production and rearrangement of carbonium ions is thought to be involved in the isomerization reaction. Next. This is the figure of butane isomerization. As you can see, the mixed butane feed enters the deep isobutanizer to separate isobutane. Then a debutanizer to separate butanes from carbon 5 impurities as illustrated in the figure. Purified butanes are combined with hydrogen and heated to 230 to 340 degrees at 200 to 300 psi under pressure. Because the catalyst is extremely sensitive to moisture, the feed must be completely dried before use. The catalyst in the low temperature first step is aluminum chloride promoted by hydrogen chloride. Hydrogen gas is then used to prevent the formation of olefins and to manage side reactions including dispropanation and cracking. The catalyst in the high temperature second stage is a noble metal such as platinum. Next. As I explained just now, butane isomerization is a two-stage process that converts N-butane to isobutane. N-butane is commonly combined with other butanes in the feed. Hydrogen gas is added to inhibit olefin formation and to control side reactions such as dispropanation and cracking. Higher temperature, lower space velocity, and lower pressure all maximize the yield of isomerization. Next. Development of isomerization process. Commercial processes have also been developed for the isomerization of low-octane normal pentane and normal hexane to higher octane isoparaffins. The limitation of this process is that it does not produce a high-octane end product that can contribute significantly to the production of unleaded gasoline. Next. Next, we're moving on to catalytic reforming. It is a hydrogenation-dehydrogenation catalyst supported on alumina or silica alumina that are used for catalytic reforming in the presence of hydrogen. The conditions required for this process is temperature at 840 to 965 degree F, pressure at 100 to 600 psi, reform of feed naphtha containing 7 or more carbons, isomerization feed pentane and hexane removed from desulfurized naphtha. Next. Catalytic reforming operates at low pressure and high temperature, which favors production of aromatics, which means higher yield. Catalyst cycles last from 6 to 12 months. The three major process flows for catalytic reforming are semi-regenerative, cyclic or fully regenerative, and third one is continuous catalyst regeneration or CCR, which is a moving bed. Next. This is the catalytic reforming reactions. The purpose of this reaction is to transform carbon 6 to carbon 11, naphthalene, and paraffins into aromatic compounds. There are four main hydrocarbon types in naphtha: paraffins, olefins, mainly from catalytic cracking and coking units, naphthenes, and aromatics. Next. Isobutane. For the figure just now, can you move to the previous slide? If the feed contains carbon 6 hydrocarbons, carcinogenic benzene is hydrogenated into cyclohexane to avoid its release into the atmosphere upon incomplete combustion or when drivers fill their automobile tanks with gasoline. The hydrogenation reaction in reforming is endothermic and thus heat is required. This figure summarizes the reactions of catalytic reforming. The purpose stated just now, that the aromatics can go to chemical plants or be used as high-octane gasoline blend stocks. For the paraffins in the feed, the acidic sites of the catalyst isomerize and paraffins in the feed to isoparaffins. This is a key step for cecilization. It is followed by dehydrogenation to form aromatic compounds. The process yields considerable amounts of hydrogen. 4 moles of hydrogen are produced from 1 mole of hexane. The hydrogen is used in hydrotreaters, hydrocrackers, isomerization units, and others. Maybe the other can continue for the next slide. Thank you.
Okay, thank you, Fika. And I will explain the next slide about alkylation. So isobutane reacts with C3 to C5 olefins, mainly from cracking units. Strong acids are produced and branch chain hydrocarbons. Without isobutane excess, C3 to C5 olefins can undergo undesirable polymerization into sludge. Now, hydrocarbons, or famously known as alkylate, is a high octane has a high octane value, 88 to 95 and 90 to 98, and low rate vapor pressures, making them an excellent contributor to the gasoline blending pool. Next. So this figure below shows the alkylation mechanism for reaction of butanes with isobutanes. So this process uses an excess of isobutane to control heat and minimize olefin polymerization. So at the reaction number 1, it exemplified in the reaction of 2-butane or its isomers protonated by the acid catalyst to form a 2-butanedium ion, which isomerates to stable T-butyl ion. And then for the next step, 2A, 2B, and 2C, we can see this shows how different isomers lead to different Ca carbocations. Ca carbocations will isomerize into more stable 2,2,4 3-methyl pentyl ion. So the most stable reaction from the three, as I can see, is 2A. Yes. And then on reaction number 3 here, the Ca carbocation ion will react with predominant amounts of isobutane through hydrate transfer to be neutralized and leave T-butyl ion for propagating the alkylation reaction. And then for the last reaction is that some of the Ca carbocation or C4 dimer ions can proceed to react with the olefins to form C12 carbocations or a C4 trimer ion and continue to polymerize to form sludge or acid soluble organics or ASO. Next. And then the figure down below shows about the alkylation reaction. Basically, this summarizes the alkylation reaction into 2,2,4 trimethylpentane, or commonly known as isooctane, and is a reference compound for gasoline octane, rating defined as 100. So next is the refinery stream flow with alkylation unit. Now, the refinery streams, how it works is that first, the isobutane feed comes from the hydrocracker, an FCC unit, or a butane isomerization unit, and then all off gases of the refinery units are sent to a gas plant for treating to remove the H2S and the NH3 to separate light hydrocarbons, including isobutane. And olefins came from thermal conversion units in the refinery, such as thermocracking, catalytic cracking, hydrocracking, and coking. So the main source of olefins is C3 and C4 from fluid catalytic cracking unit, or the FCC. Next. And then this picture shows about the alkylation plant flow. Now, the alkylation plant flow is a highly exothermic reaction. Now, the mixed feed of isobutane and cracked gas containing olefins is chilled to a low temperature before entering the reactor. This decreases the polymerization of the olefins. And then acid is recovered and recycled. The product is caustic washed to remove the residual acid from the product. And then the product stream goes through the depropanizer to separate the propane to the isobutanizer to recover isobutane for reuse, and to the butanizer to separate butane from the desired product alkylate. So from this plant flow, we will get alkylate or the hydrocarbon. Now, what is alkylate? Alkylate is an ideal gasoline component that has an octane number exceeding 90, and it has been the main process for improving the octane of aviation gasoline. It has zero sulfur, zero benzene, and zero olefin concentration, which means that alkylate is eco-friendly. Low rate vapor pressure reduces the hydrocarbon emissions. Now, there are two types of alkylate that employs in the process, which the first one that employs the hydrofluoric acid or hydrofluoric acid alkylation unit, HAAU, or it employs the sulfuric acid or the sulfuric acid alkylation unit, SAAU. Now, alkylate runs at low temperatures to avoid polymerization of the olefins, as explained before, and the temperature that requires for hydrofluoric acid catalyzed reaction is about 21 until 38 degrees Celsius, while sulfuric acid is lower than that, about 2 to 10 degrees Celsius, and requires food refrigeration. Next. Now I will explain about the hydrofluoric acid alkylation process. Now HF is a dangerous, and extra precaution are taken to ensure that it is always contained. So the feed is mixed with recycled isobutane to give an isobutane olefin ratio of 15:1. And then the combination is introduced to the reactor at the temperature of 70 to 100 Fahrenheit, or about 21 until 38 Celsius. And there it reacts in the presence of high purity above 88%. The product mixture is sent to the settler and an acid stripper to recover the acid, which is hydrofluoric acid. And then at the bottom of the stripper is sent to the deisobutanizer to recover isobutane. A depropanizer is used to purify the isobutane. And then lastly, the product stream, which enters the defluorination before it enters the butanizer for separating N-butane from the final product, alkylate. And this is the reactor that was created by an American company, if I'm not mistaken. It's the Philip HF alkylation reaction. Now, the Phillips discovered a single column of HF alkylation reactor, and the way how it works is that the isobutane and olefin feed is mixed with the acid in the reactor pipe at about 21 to 38 degrees Celsius. And then the acid flows down a side pipe by gravity without a pump for returning to the reactor pipe after cooling. And then hydrocarbon products mixture flows out at the top of the settler. A single tower can be used for fractionation of the product mixture. And then the propane comes off as an overhead. And isobutane recycles and is withdrawn several trays before the feed tray. And then the N-butane is taken off as a vapor several trays below the feed tray. And as alkylate flows at the bottom, the product flows at the bottom. Next. Now I will explain to you about the sulfuric acid alkylation. Now this figure shows about the auto refrigeration sulfuric acid alkylation unit. Now the steps are: the olefin feed is mixed through with isobutane and acid and chilled for 35 to 45 Fahrenheit, which is about 2 to 10 to around 7-8 degrees Celsius, and through the heat exchanger for minimizing redox reaction and preventing tar and SO2 formation. And then the pressure is at 5 to 15 psi and applied to prevent the vaporization. And propane is a lighter gas are withdrawn at the top of the reactor, and the gases are compressed and liquefied. A portion of this liquid is vaporized in an economizer to cool the olefin feed as an auto refrigeration before it's sent to the reactor to the propanizer. And then the C-force and alkylate mixture is sent to the isobutanizer after caustic wash to remove residual acid to fractionate into isobutane for recycling into isobutane feed of N-butane and alkylate, and that are the final products, N-butane and alkylate. Next. And then there is the Stratco effluent refrigeration process. This is another method about sulfuric acid alkylation. Now, a typical Stratco effluent refrigerated sulfuric acid alkylation, which uses acid saddler effluent as the refrigerant to provide cooling in the contractor reactor. The Stratco contractor reactor is a horizontal pressure vessel containing an inner circulation tube, a tube bundle to remove the heat reaction, and a mixing impeller. Now, how this works is that the carbon feed and recycled acid enters to the suction side of the impeller side in the circulation tube. As the feeds pass across the impeller, a fine emulsion of hydrocarbon and acid is formed by extremely high shear forces induced by the impeller. Heat transfer from the reaction side of the tube bundle to the refrigeration side is aided by the high circulation rate, which also prevents any significant temperature differential within the contractor reactor. A portion of the circulating emulsion in the contractor reactor flows from the circulation tube on the discharge side of the impeller to the acid saddler, where hydrocarbon phase is separated from the circulating acid phase area. And then the acid is recycled back to the contractor, and hydrocarbon leaves and leaves the settler and is let down across back pressure control valve to the tube side of the contractor reactor bundle and the heat reaction from the shell side. I think Zaki can continue the presentation. Thank you.
Okay, maybe now I'm going to explain about the ionic liquid alkylation process. So first, an ethylene containing refinery stream is fed to an ethylene extraction.
Jackie, your voice can be more loudly because it's very low.
Am I clear? Or is it still?
Yeah, still low. Can you up the volume?
Is it okay now?
Yeah, no problem. Okay.
So the first step, an ethylene containing refinery stream is fed to an ethylene extraction unit to separate C2 plus fraction rich in ethylene. Then the ethylene extraction unit is typically comprised of membrane and or distillation column separation equipment. Then a secondary refinery stream containing isopentane is fed to a distillation zone. Then the streams enriched in ethylene and isopentane are contacted in the presence of an ionic liquid catalyst in a reactor under alkylation conditions. Then the catalyst and hydrocarbon phases are separated in a catalyst separator, and the catalyst is recycled back to the reactor. Then a portion of the recycling catalyst is sent to a slipstream catalyst regeneration unit, and then finally the hydrocarbon phase is sent to a distillation zone to recover unreacted isopentane for recycle, and the alkali product is collected at the bottom. Next, I'm going to explain about the zeolite catalyzed alkylation process. So it has been proposed that protonation of an olefin by zeolite Bronsted acid sites results in formation of stable covalent alkoxide intermediates. So the first step, the alkylation reaction catalyzed by zeolite is initiated with protonation of N-butane on a Bronsted acid site to form C4 carbocation. This is followed by addition of an olefin on the C4 carbocation to form C8 carbocation. Then when a hydrogen atom attached to a highly substituted carbon atom in an isobutane molecule is attacked by surface bonded C8 carbocations, a hydride ion transfer between them occurs, resulting in isooctanes and C4 carbocation. And then further C8 carbocations can oligomerize with olefins to form heavier hydrocarbons. And then I'm going to explain about polymerization. So polymerization is basically a process through which a large number of monomer molecules react together to form a polymer. The macromolecules produced from a polymerization may have a linear or branched structure. They can also assume the shape of a complex three-dimensional network. There exist several different categories of polymerization reactions, which are step growth polymerization, chain growth polymerization, and condensation polymerization. A polymer is a substance that is made up of very large molecules that are in turn made up of many repeating units called monomers. Polymerization is the process through which these monomers come together to form the macromolecules that constitute polymers. An illustration detailing the polymerization of the monomer styrene into the polymer known as polystyrene is provided below. So this is the picture of the polymerization of styrene. So then I'm going to explain about the mechanism of polymerization. So generally, polymerization consists of 3 steps, which include initiation, propagation, and termination. As for the reaction mechanism, the process of polymerization mainly involves 2 different methods. These include the step growth mechanism and chain growth mechanism. Here I'm going to explain about the step growth polymerization, condensation polymerization, and chain growth polymerization. So first, in the step growth polymerization, the polymers are formed by the independent reaction between the functional groups of simple monomer units. In step growth, each step may consist of a combination of 2 polymers having a different or same length to form a longer length molecule. The reaction is a lengthy process and the molecular mass is increased at a very slow rate. An example of step growth polymerization is condensation polymerization, where a water molecule is evolved in the reaction when the chain is length. As for the condensation polymerization, the formation of the polymer occurs where there is a loss of some small molecules as byproducts through the reaction where molecules are joined together. The byproducts formed may be water or hydrogen chloride. Polyamide and proteins are examples of condensation polymers. And then the last is the chain growth polymerization. So the molecules of the monomers are added together to form a large chain. The monomers uh, adding may be the same type or different. Generally, alkylanes, alkadiens, and their derivatives are used. In this mode, lengthening of chains occurs as a result of the formation of either free radicals or ionic species. I think that's all from us. Thank you for your attention.